Welcome back to The Discoverers. We have reached the last chapter. This is chapter 82, The Infinite and the Infinitesimal. From Hiroshima on August 6, 1945, the world received the shocking discovery that man had opened the dark continent of the atom. Its mysteries would haunt the 20th century. Yet for 2,000 years, the atom had been the most arcane of philosophers' concerns. The Greek word atomos meant the smallest unit of matter, supposed to be indestructible. Now atom was a household word, a threat and a promise without precedent. The first atomic philosopher was a legendary Greek, Leucippus, suspected to have lived in the 5th century BC. Democritus, his pupil who gave to atomism its classic form as a philosophy, was so amused at human follies that he was known as the laughing philosopher. Yet he was one of the first to argue against mankind's decline from a mythical golden age, and to preach a gospel of progress. If the whole universe consisted only of atoms and void, it was not infinitely complex, but somehow intelligible, and there might be no limit to man's power. In one of the greatest Latin poems, De Rerum Natura, Lucretius, circa 95 BC to circa 55 BC, perpetuated ancient atomism. Aiming to free people from fear of the gods, he showed that the whole world was made of void and atoms that moved by their own laws, that the soul died with the body, and that therefore there was no reason to fear death or supernatural powers. Understanding nature, he said, was the only way to peace of mind. The Church Fathers, committed to the Christian afterlife, attacked Lucretius, and he was ignored or forgotten during the Middle Ages, but became one of the most influential figures in the Renaissance. So atomism first entered the modern world as a system of philosophy. Just as the Pythagorean symmetry provided a framework for Copernicus, just as geometry enticed Kepler, and as the Aristotelian perfect circle charmed Harvey, so the philosophers' indestructible atoms appealed to chemists and physicists. Quote, "The theory of Democritus relating to atoms," Francis Bacon observed, "is, if not true, at least applicable with excellent effect to the exposition of nature." End of quote. Descartes, 1596 to 1650, invented his own notion of infinitely small particles moving through a medium he called the ether. Another French philosopher, Pierre Gassendi, 1592 to 1655, seemed to confirm Democritus and offered still another version of atomism, which Robert Boyle, 1627 to 1691, adapted to chemistry, proving that the proverbial elements, earth, air, fire, and water, were not elementary at all. The prophetic insights of a Jesuit mathematician R.G. Boscovich, 1711 to 1787, charted paths for a new science of atomic physics. His bold notion of quote-unquote point centers abandoned the old concept of an assortment of different solid atoms. The fundamental particles of matter, he suggested, were all identical, and matter was the spatial relations around these point centers. Boscovich, coming to these notions from mathematics and astronomy, foreshadowed the increasingly intimate connection between the structure of the atom and the structure of the universe, between the infinitesimal and the infinite. The experimental path into the atom was charted by John Dalton, 1766 to 1844, a self-educated Quaker amateur who picked up suggestive notion from Lavoisier, 1743 to 1794. A founder of modern chemistry, Lavoisier brought atomic theory back to earth when he finally made the atom a useful laboratory concept by defining an element as a substance that could not be broken down into other substances by any known method. Born to a family of weavers in Cumberland, in the English Lake District, Dalton carried the mark of his modest origins all his life. At 12, he had taken charge of the Quaker school in the village. When he went on to teach in the nearby Kendall, in the school library, he found copies of Newton's Principia, Boyle's Works, and Buffon's Natural History, along with a 2-foot reflecting telescope and a double microscope. There he came under the spell of a phenomenal blind natural philosopher, John Gough, who, Dalton wrote a friend, quote, understands well all the different branches of mathematics. He knows by the touch, taste, and smell almost every plant within 20 miles of this place, end of quote. He would be celebrated by Wordsworth in his Excursion. From Gough, Dalton received his basic education in Latin, Greek, and French, his introduction to mathematics, astronomy, and all observational science. Following Gough's example, Dalton began keeping a daily meteorological record, which he continued until the day he died. When dissenters set up their own new college in Manchester, Dalton became professor of mathematics and natural philosophy. In the Manchester Literary and Philosophical Society, he found an eager audience for his experiments. To them he offered his, quote, extraordinary facts relating to the vision of colors, end of quote, probably the first systematic work on color blindness, from which John and his brother Jonathan both suffered. Quote, having been in my progress so often misled by taking for granted the results of others, I have determined to write as little as possible but what I can attest by my own experience, end of quote. He observed the aurora borealis, suggested the origins of the trade winds, the causes of clouds and of rainfall, and incidentally made improvements in rain gauges, barometers, thermometers, and hygrometers. Dalton's interest in the atmosphere provided the approach to chemistry that led him to the atom. Newton had expected the smallest invisible bodies to follow the quantitative laws governing the largest heavenly bodies. Chemistry would recapitulate astronomy. But how was man to grasp and measure the movements and mutual attractions of these invisible particles? In his Principia, Newton had speculated that phenomena of nature not described in that book, quote, may all depend on certain forces by which the particles of bodies, by some causes hitherto unknown, are either mutually impelled towards one another and cohere in regular figures, or are repelled and recede from one another. End of quote. Dalton went in search of these primitive particles, seeking some experimental way to encompass them in a quantitative scheme. Since gases were the loosest, most mobile form of matter, Dalton focused on the atmosphere, the mixture of gases that comprised the air, which provided the point of departure for all his thinking about atoms. Quote, why does water not admit its bulk of every gas alike? End of quote. He asked his colleagues in 1803 in the Manchester Literary and Philosophical Society. Quote, I am nearly persuaded that the circumstance depends upon the weight and number of the ultimate particles of the several gases, those whose particles are lightest and single being least absorbable, and the others more according as they increase in weight and complexity. End of quote. Dalton had discovered that contrary to the prevailing view, the air was not a single vast chemical solvent, but a mixture of gases, each of which remained distinct and acted independently. The product of his experiments was his epoch-making table of the relative weights of ultimate particles of gaseous and other bodies. Taking hydrogen as one, he itemized 21 substances, depicting the invisible ultimate particles as tiny solid balls like pieces of shot but much smaller. He proposed to apply to them the Newtonian laws of the attractive forces of matter. He aimed at, quote, a new view of the first principles of elements of bodies and their combinations, which I doubt not will in time produce the most important changes in the system of chemistry and reduce the whole to a science of great simplicity and intelligible to the meanest understanding, end of quote. When he showed a, quote, particle of air resting on 4 particles of water, end of quote, like, quote, a square pile of shot, end of quote, with each tiny globe touching its neighbors, he provided the ball and spoke model for organic chemistry in the century to come. For his popular lectures, Dalton invented his own, quote, arbitrary marks as signs chosen to represent the several chemical elements or ultimate particles, end of quote, displayed in a table of atomic weights. Of course, Dalton was not the first to use a shorthand for chemical substances. The alchemists had theirs, but he was probably the first to use such symbolism in a quantitative system of ultimate particles. Making an atom of hydrogen his unit, he calculated the weight of molecules as the sum of the weights of component atoms, and so supplied a modern syntax for chemistry. The actual abbreviations using the first letter of each element's Latin name, H2O, etc., were designed by the Swedish chemist Berzelius, 1778 to 1848. The first reception of Dalton's atomic theory was anything but enthusiastic. The great Sir Humphrey Davy quickly dismissed his notions as, quote, rather more ingenious than important, end of quote. But Dalton's ideas, elaborated in A New System of Chemical Philosophy in 1808, were so persuasive that he was awarded the Royal Medal in 1826. Never forgetting his plebeian origins, he still remained aloof from the Royal Society in London, but was elected without his consent in 1822. Suspicious of the Society's aristocratic, dilettante tone, he felt more at home in Manchester, where he did most of his work, and he joined with Charles Babbage and helped found the British Association for the Advancement of Science to bring science to all the people. Theologically orthodox Newtonians would not believe that God had necessarily made his invisible ultimate particles invariable or indestructible. They shared Newton's suspicion that God had used his power, quote, to vary the laws of nature and make worlds of several sorts in several parts of the universe, end of quote. Dalton's indestructible atom became the foundation of a rising science of chemistry, providing elementary principles, its laws of constant composition and of multiple proportions, its combination of chemical elements in the simple ratio of their atomic weights. Quote, chemical analysis and synthesis go no farther than to the separation of particles one from another, and their reunion, Dalton insisted. No new creation or destruction of matter is within the reach of chemical agency. We might as well attempt to introduce a new planet into the solar system, or annihilate one already in existence, as to create or destroy a particle of hydrogen, end of quote. He continued to use the laws of visible heavenly bodies as his clues to the infinitesimal universe. The prophetic Sir Humphrey Davy still remained unconvinced. Quote, there is no reason, he said, to suppose that any real indestructible principle has yet been discovered. End of quote. And there we will conclude part 1 of our last chapter.